Okay, so now we're going to be talking about drawing Lewis dot structures. Time to focus. Over here, guys. Shh. You also need to refer to the periodic table because we have to start off with the first rule here, which is counting the total number of valence electrons. So, counting the total number of valence electrons, you're going to flip your paper over. We're going to work on the examples, and I'm going to flip back and forth and show you the rules so you don't have to keep flipping yourself. So, here, we're going to look. First example, AsCl3, arsenic trichloride. Now, it said to count up all of the valence electrons represented in the structure. So we're going to start here. We're going to look at arsenic, and its position on the periodic table tells me it has how many valence electrons. It's in group 15 or 5A, the nitrogen group, so that means it's going to have 5 valence electrons. Very good. Now, the chlorines. How many of them are there in this compound?
3.
3. And each chlorine brings how many valence electrons to the structure? Chlorine is a halogen. It's in group 17 or 7A.
7.
So it should be 7. Thank you. That's a total of 21. Now we need to add up our total. So we have 5 plus 21 gives us a total of 26 valence electrons. So that is the first thing you always do when trying to draw a Lewis dot structure is count the number of valence electrons. So that was step 1. You don't have to flip, I'm going to flip for you. Step 2 says identify the central atom. Identify the central atom. It is usually the first atom in the compound. It cannot be hydrogen ever. It cannot be hydrogen because hydrogen can only form one single bond. Like it can form one single bond like so. A single bond is sharing 2 electrons. You can represent a single bond either using just a line, 1 dash, or you could do 2 dots between. Either way, it doesn't really matter. You can draw them either way. But hydrogen only can form one bond where it shares 2 electrons, so it looks like helium. Hydrogen will never be in the middle, ever. Then we're also looking for the least electronegative element, but usually in our compounds they write the least electronegative element first. So you're going to see that anyways. So if we're looking at our compound, which element is written first? Arsenic. Now you can check the electronegativity. Remember, electronegativity increases if you go up the group and across the period, but arsenic should go in the middle. So that's step 2. Step 1 was counting the electrons. Step 2 is now deciding on the central atom. Okay. Step 3. Draw single bonds to all the ligands. Now, draw single bonds. Single bonds are a pair of electrons. What are ligands? Ligands are the elements surrounding the central atom. So in this case, our ligands are going to be chlorines. The other 3 atoms in this compound are going to surround the arsenic. So let's go ahead and attach them by single bonds. Okay, so I attached all of my chlorines using single bonds. And I have also used some of my 26 electrons now to create those single bonds. Each single bond is worth 2. 2, 4, 6. So now I'm down to 20 valence electrons. I do also want to show you over here that you could draw it this way too. Like I said, you could use the dots instead, like so, to connect them. 1 dash means 2 dots, so you can use the 2 dot representation or you can use the dash representation. Either way is acceptable. Okay? Now, so we've attached our ligands or the chlorines. Question?
How do you figure out it's 2 for
Well, we're just attaching the ligands to the central atom by a single bond. And a single bond, by definition, has 2 valence electrons in it. A dash represents 2 electrons, or you can use the 2 dots to represent them. Either or, it's fine. All right, now let's go back to the satisfy the octet rule for the ligands by adding lone pairs. So let me show you what lone pairs means. These are our ligands, our chlorines are our ligands. So I'm going to satisfy their octets. They need 8 in order to mimic the nearest noble gas. So I put them in pairs. That's 2, 4, 6. Now how many electrons have I used? 6 of my 20, so now I'm down to how many? I have 14 left. Let me keep satisfying the ligand here. 2, 4, 6. So now I'm down to 8. We have 8 left. And the last one, 2, 4, 6. Now I'm down to 2. Okay, I've satisfied all the octets of the ligands. And how do we count them around the ligands? 2, 4, 6, 8. So there's 8 around here. 2, 4, 6, 8. 2, 4, 6, 8. Okay, so all of them need to have 8 except for hydrogen. Remember, hydrogen only needs 2. So let's go back to our rules. We satisfy the octets of the ligands. Now, double check, count all the electrons in the drawing. If you have all the electron dots you need, move on to step 6. Did we put all the electrons out? No, we still have 2 extra. If you have more electrons to add them to the central atom. So that last pair we're going to add to the arsenic. And look, arsenic needs 2 anyways. We're going to add it to arsenic. So now it's 2, 4, 6, 8 around the arsenic. Okay? Now we double check our structure, make sure everybody has 8. So we have 2 here, 2 here, 2 here, 2 here, 2, 2, 2, 2, 2, 2, 2, 2. Yes, everybody has 8. 2, 4, 6, 8 around the arsenic. So that would be the dot structure for arsenic trichloride. Now over here on this one, you would just do the same thing. The only difference is instead of having a line between them, connecting them as representing the bonded pair of electrons, you use 2 dots like so. But this would end up being the same thing over here, because you would have satisfied the ligands and then added the lone pair to the central atom like so. Either representation is acceptable. You can use dots or you can use the lines and dots. All right, so that's one example where we got to stop because we used all of our electrons and everybody was satisfied with 8. But let's look at an example that may not work out so easily. SiF2O. So step 1 means we need to do what? Figure out the valence electrons. Let's do that. Si gives us how many?
4.
4. F gives us 7, and there's how many in here? Multiply by 2, so we get 14, and our O brings in 6. So let's count them all up then. We have 4 plus 14 plus 6 gives us, that gives us 24 valence electrons. Good. And now, based off our central atom rules, which one will we pick to go in the center? Silicon. It's the first element. You could look for electronegativity, but it's usually the first one unless it's hydrogen. So let's put Si in the middle. After we figure out the central atom, what's next? Attach the... What are the things that go around the central atom called? The ligands. So attach the ligands. In this case, we have 2 fluorine ligands and we have 1 oxygen ligand. So let's attach them. Fluorine, fluorine, and oxygen. Sorry, now I kicked it. All right. How many electrons did I use to pair them up and put them onto this dot structure? I used 6. So out of my available amount, I'm now down to 18. The next step is to do what? After we've attached them, we now have to satisfy their octet. So let's do that. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, that works out nicely because we had how many left? 18. Now we're down to 0. Up. Does anybody see a problem? What is the problem here? Silicon only has 6, does not have 8. So now, let's go back to our rules and see what it says to do when we run out. So here we're on B. We've run out of electrons. It says, now that all of the dots are present, see if the central atom satisfies the octet. And we know it's not satisfied for silicon, so we have to do B here. If no, draw coordinate covalent bonds, which are double or triple from lone pairs on the ligands to make sure the central atom has 8. So we're going to take off a lone pair of one of the ligands, and we're going to move it and make it become, say, a double bond with 2 lines or 4 dots, or a triple bond. We do it twice. We make a triple bond if needed. So the problem is that we need to decide which ligand to pull it from. Do we pull it from the F or the O? Well, down here, I put some things to remember. Hydrogen always has 2. Carbon, nitrogen, oxygen, fluorines will always follow the octet rule with 8. That means in general, carbon atoms form up to 4 bonds. Nitrogen forms up to 3 bonds and has 1 lone pair. Oxygen can form up to 2 bonds and will have 2 lone pairs. This boron example, boron will often only have 6. That's another little nuance we'll discuss later. But number 4 here, the halogens will only have single bonds when ligands, when they're not central atoms. So fluorine can only have a single bond. Can we pull from fluorine? No. So we have to pull from oxygen, but it does say oxygen can form up to 2 bonds. So we'll go ahead and pull from our oxygen here. So looking here, I'm going to take off one of my pairs of electrons, and I'm going to basically move it over here and make it a double bond. So if we count everything now, this is 2, 4, 6, 8 around the silicon. The fluorines have 6, and plus this one right here, the 6 and this one. Oxygen has 1, 2, and then the 2 lone pairs also has 8. Does everybody have 8 now? Yes, so this would be the drawing and dot structure for this particular one. Okay? Okay, so hopefully we've counted up our dots for the next one. Let's take a look here. We have 4 for the carbon, 5 for the nitrogen, and the bromine brings in 7, so that's a total of 16 valence electrons. Who goes in the center? Carbon. And we attach our ligands. So then we attach nitrogen and we attach our bromine. Okay? Now, how many electrons did I use to attach them? 4. So now we're down to, we have 12 left. We're going to satisfy the octet of the ligands. Okay? And I just used the rest of the 12 there, so now we're down to 0 again. Up, we see another problem here. Which atom is not stable? Carbon does not have 8 and carbon is not stable. So, out of our choices to pull from, we have bromine and we have nitrogen. Can bromine form more than the 1 bond? Bromine is a halogen, and so when it's a ligand, it's only going to have 1 single bond. What did it say about nitrogen? Nitrogen could form up to 3 bonds. So nitrogen can do more bonding, so let's pull from nitrogen. So Take one off, and we go ahead and double bond it. Does that satisfy carbon? No. So in this case, we have to pull one more off and draw in a triple bond. And therefore, now the nitrogen has 2, 4, 6, 8. They're sharing 6 in the middle. Carbon has 2, 4, 6, 8, sharing the 6 in the middle between carbon and nitrogen. And the bromine has a single bond and then 6 more in its lone pair, so it also has 8. Everybody is now satisfied. Good so far? Yes, try the SO3 one. Set it up. I'll be walking around. All right, looking at SO3, most of you got it correct. But I just wanted to go over it. S brings in 6. Each oxygen brings in 6. There's 3 of them, so that's 18. This is a total of 24 valence electrons. Sulfur goes in the center. Add your ligands. Now we satisfy the octets of the ligands. A total of 18, so now we've ran out because we had already used 6, so we had 18 left. Now we've used the rest of them, so now we're down to 0. Doesn't really matter which oxygen you choose to pull from. You could have pulled from any of them. I'll just take the ones from down here and double bond it here. But if you chose to double bond a different one, like you double bonded that one and left those single, it's still correct. It's not a problem. Question?
What if you had like fluorine for all 3 and you used the middle one?
Well, that wouldn't happen in that particular case. There would be enough electrons so that everything could remain single bonded in that particular case. Okay? So, now I want to look at the diatomic elements. So let's look at the diatomic side. Get that one out, please. Okay, so diatomic, remember what that prefix di means? What does that mean?
2.
It means 2. And since atomic comes after it, what do you think that means? 2 atoms. Remember, our diatomic elements are twins. Like oxygen is O2. We don't breathe in O, we breathe in O2. So when you're writing a chemical formula, it should be like F2. Should be Cl2. Bromine is Br2. Iodine, oxygen. Oh, that's hydrogen. Oh, that is rich. That one's hydrogen. This one's oxygen, and so forth. Now, remember you're supposed to know all of 7 of the diatomics. You can use Dr. Brinkelhoff as your way of remembering, or you can use the 7 rule. So remember Brinkelhoff. You can remember it that way, or you can use the 7 rule off the periodic table. Start at 7, make a 7. Don't forget hydrogen's the 7th. When you're drawing the dot structures, you'll need to count your electrons again. So I'll do it over here. For fluorine, we have 7 valence electrons. There's 2 of them, so a total of 14 to work with. There's only 2 atoms in this particular molecule, and it is still a molecule. It's just not a compound, because remember, a compound has to have 2 different elements in it in order to be that. So what you start off doing is you attach them to each other by a single bond. So I've used 2 electrons. Now I'm down to 12. Then all I need to do is satisfy the octets, so I'm going to start doing that. 2, 4, 6, 8, 10, 12. Oh, that's perfect. I ran out. I have 0. Does each fluorine now have 8? Yes, so that one is done. I wanted to show you hydrogen as well. So you can remember that hydrogen only forms single bonds. Hydrogen is above lithium in the group, so how many valence electrons is hydrogen going to have? It's above the alkali metals. The alkali metals have 1. So 1 times 2 because there's 2 hydrogens. That's 2 valence electrons that we're dealing with. And since hydrogen only needs 2 to be stable because that makes it look just like helium, all you have to do is put 1 line between them. They're sharing that pair of electrons, and now hydrogen is stable. But looking at, say, oxygen, because not all the diatomics are that easy. Let's look at oxygen. How many valence electrons does each oxygen bring in? 6, and there's 2 of them, so that's a total of 12. Well, we take our oxygen, we attach it to the other oxygen, so now I've used 2, down to 10 now. I do 2, 4, 6, 8, 10. Uh-oh, I ran out. Does anybody have any ideas?
Yes.
We need to double bond it. So I'm going to pull from this side, take 1 off, and create that double bond. So not all the diatomics are single bonded. Do take a moment to figure it out. There's also some on the back that I want to show you real quick. An example. Like for instance, N2H4. This is an interesting one because it has more than one central atom. N2H4 implies that both ends are going to be in the middle. Let's count our electrons first though. The nitrogen has 5 and there are 2 each, so 10. The hydrogens have 1 and there's 4 of them, so that's 4. So this is a total of 4 plus 10 gives us 14. I'm going to put the nitrogens together in the center, like so. So when you have 2 central atoms, put them in the center like so. Hydrogen can't ever go in the middle, so we can't do that. So now I'm down to 12 valence electrons. But the hydrogens, there's 4 of them. That's an even number. Does anybody have a suggestion as to how to arrange them? How should we put them? So we should put 2 on each nitrogen and equally distribute them? Yeah, that's a great idea. That's what we're going to do. Put 1 on 2 on that nitrogen, so now I'm down to 8. Put 1 here, 1 here, now I'm down to 4. Okay, so when you see that where there's that even number of hydrogen, they usually equally distribute to both central atoms. Okay, now we're not done though. We have 4 electrons, and where do we put them when we have extra? They go on the central atom. So 2 down to 2, 2 down to 2. Does everybody have their necessary numbers? The nitrogens have 8, 2, 4, 6, 8. Each hydrogen has 2. Everybody is happy. Now what you should notice about this top area is that all of it, and everybody in 1 through the top area, section 1, they're all single bonded ones. You're not going to see any doubles or triples in there. The middle section though is going to have 1 multiple bond. So it's either going to be a double or triple, but at least 1 in there. The bottom section is just miscellaneous, so I mixed them up in there. So I'm going to give you some time to practice. Walk around, and if you have any questions, let me know.